Let's discuss the subject of putting something inside the capacitor known as the dielectric. The presence of the dielectric serves two purposes. One is, of course, to keep the charges apart from each other. Now remember, the capacitor has got net charge 0, which means if this plate has got positive charge, the other plate has got equal and opposite negative charge. If you bring those two plates together, the capacitors will short itself and your net charge will be 0. So we cannot have that. Therefore, putting some material inside provides structural integrity for the capacitor. This material is called the dielectric, and the dielectric constant, which is a number, is denoted by the Greek letter kappa. Even though that looks like a K, it's supposed to be the Greek letter kappa. Now that's the lowercase kappa. The uppercase kappa looks like a capital K. We will not be using the uppercase kappa until we come to magnetic fields. So I want to tell you what happens to the capacitance of a capacitor. By the way, this is the symbol of a battery. A long terminal is a positive side and the short terminal is a negative side, and that's why I put plus Q on the plate that's attached to the long terminal and minus Q on the plate attached to the short terminal. Now I'm going to first show you a good way of writing this circuit. It's called a tree diagram. And what I do is I separate out the long and the short portions of the battery. I put the long portion on the top as a positive value, and then I put the capacitor here. The negative terminal is sent to the earth through a ground. This is called a tree diagram of that circuit. Tree diagrams will play a useful role in analyzing the circuits in circuit analysis later on in this course. So I have put some dielectric inside this capacitor. What happens to it? Actually, what happens is that the capacitance of the capacitor increases. So if I have the capacitance, now the symbol of a capacitor, by the way, is a parallel plate, going to show that parallel plate capacitors are the most important. The capacitance of a parallel plate capacitor is given by the formula epsilon naught, the area of the plate, this could be one of the plates, not both the plates, just one of them, divided by the distance d that separates the two plates. That's the distance d, and that's the area of either the top plate or the bottom plate. That's the normal capacitance of a capacitor without anything in it. Now when you put a dielectric in it, the only effect is to make the capacitance become kappa times epsilon naught A over D. And for your information, kappa is bigger than 1 always. The smallest value of kappa is that of the vacuum, which is exactly equal to 1. And anything other than vacuum, even air, for example, is more than 1. But air is so close to vacuum that we don't truly consider air as a possibility. We have to put something inside for it to be truly a dielectric. For example, water has got a kappa of about 80, depending on its purity, which means that if you take you can't just throw water into the capacitor, it'll short it. But if you take a bag and put water in it and then put the bag in between the capacitors plates, then the capacitance of the capacitor will increase 80-fold. And there are materials that increase it several hundred times. So it's to our advantage to have these capacitors filled with material. All right, now let's talk about another way to adjust the value of a capacitance. Now when you try to build anything in electronic hobby, you're not going to find the exact capacitance that you need from Parts Express or some other place. So you have to make up arrangements of capacitors. And there are two popular arrangements, series and parallel. And then of course you can mix them up. You can have two in series and that in parallel with the next one. So you can really mix it up. So let's study the combinations. And after I've done the combinations, I'll do an example on this side. So the series and parallel combinations are very simple in nature. Series means one follows the other, like the freight trains, trucks. So let me draw a series combination here. I have a source of voltage. I'm drawing the tree diagram. That's the first capacitor, and that's the second capacitor. And then that's the negative terminal or the earth. Now, for the purposes of analysis, I'll not put any dielectric inside, but you know what's going to happen. If I put a dielectric inside, it simply gets multiplied by kappa, so that's not a big deal. Let's figure out something interesting about the series combination. You observe this letter H that I have. It looks like H if you look at it from sideways. And that letter H is suspended in the middle of nowhere. So I like to call that a neutral metal island. It's not touching either plate. So that's a neutral metal island, which means that it is unaffected by what goes around it. If this capacitance on the top plate gets plus Q and that capacitor on the bottom plate gets minus Q, then the metal island will adjust itself so that the net charge is still zero. So what's going to happen? Plus Q is over there. Minus Q is going to arrange itself here. Well, that minus Q has to have come from somewhere. So there'll be plus Q on this side, so that the net charge of that neutral metal island will always remain zero. So you have no option but to conclude that in a series arrangement, the charges have to be the same. Now, my ambition, because I could not find the capacitors I want from Parts Express, is to combine these two to make it an equivalent capacitance, which I will call C sub S. So let's call that C1 and C2. And I want to combine that and find out what C sub S is. Let's try to do this. The charges are the same, so the net charge of the final product is also going to be plus Q and minus Q. So I have that the charges are the same for both of them. We learn nothing. But what about the voltage? Now, for a capacitor, remember that the capacitance of a capacitor is given by the charge Q divided by the change in voltage. Change in voltage is just the voltage. So that's the governing equation for a capacitor. That means the voltage is given by Q over C by rearranging. Now, I certainly have this voltage going from that side of the battery to this side of the battery. This has a total voltage of V. Well, this one has to hop. It's got a voltage V1 going from the battery top to the middle of the island, and then it's got a voltage hop V2 going all the way down to the earth. So I need to have that V equals V1 plus V2 because energy is conserved. Now I can write my expressions. So the charge Q over the effective series capacitance is equal to the charge Q over C1 for V1 and the charge Q divided by C2 for V2. Cancelling out the Q's, I have this beautiful expression 1 over C1 plus 1 over C2. Objects that add like this are said to add harmonically. So this is called a harmonic addition. Harmonic addition is not very strange in your lives. You have actually done it before. So it's usually used when you have to divide one piece of work between several people. So suppose you have two people, let's call them Joe and Schmo, and Joe can mow your yard in, let's say, 20 minutes, and Schmo can mow your yard in 30 minutes. How quickly will your yard be mowed if you hire Joe and Schmo together? The correct way to find out that time is 1 over t equals 1 over 20 plus 1 over 30, and then you find out what t is. It'll turn out to be smaller than either 20 or 30. It has to be, otherwise there's no point in hiring both of them. If it turns out to be bigger than either 20 or 30, then you'll just hire one or the other. But it turns out to be smaller than either one. So that's also the feature of series capacitors. This capacitances in series are going to be smaller than either one. So if you want a capacitance that's really weak, but you have two capacitors from Parts Express that are really strong, the best way to make them weak is to put them in series. Okay. So another way of writing this expression is to take the common denominator, and this is how I'm going to use it. So C1 plus C2 divided by C1 C2, and then invert it. When I invert it, I get CS equals C1 C2 divided by C1 plus C2. That's a nifty little expression to have in problems, because then you can basically do the calculation really quickly. Here you'll have to first find the reciprocal and then invert it. That takes time. Now the next arrangement of capacitors is called the parallel capacitor arrangement. So here we do the following. Now remember, we want to get a stronger capacitance, and this is how you do it. You have a capacitor that you attach like this. So the word parallel clearly is becoming meaningful because these two suffer the same drop in voltage, and we're going to say that this is equivalent to having just one capacitor whose capacitance is equal to C sub P. You can literally see what's going on here. If I extend this plate to join the top plates together, and I extend the bottom plate to join it to the bottom plate, it's essentially become that. So you can see that the capacitors are simply going to add. Well, what's the formal proof of this fact? Let's write down the equations for this. That's C1, that's C2. C1 is going to have a charge Q1, and of course minus Q1 on this side. And C2 is going to have a charge Q2 and minus Q2. Remember, the charges can be different because these two plates are not in communication. So the one thing that has to be the same in all these cases is the total charge of the final product, Q, must be equal to Q1 plus Q2, because remember, I'm joining the two plates. That's how I'm getting from here to there. So let me start with that principle. Q equals Q1 plus Q2. This time I'm going to use the capacitance, basic capacitance definition equation in the form Q equals C times V by multiplying both sides by V. Now let me substitute it here. I get CV equals Q1, which is C1V. I won't write C1V1 because this entire thing hops by V, plus C2 times V. This time we cancel out the voltages, whereas previously we canceled out the charge. Okay, and then I get C equals C1 plus C2. That's exactly what you expect. You get a stronger capacitor with more capacitance. So if you want a stronger capacitance and you don't have the appropriate capacitors at hand in your parts bin, you know what to do. That's just regular addition. No big deal. So the example I promised is a partial dielectric. Now the dielectric that I have there completely stuffs the two plates. What if that's not true? What if I have a situation where the dielectric only covers half of it? Well, that could happen. You have a dielectric, you didn't buy enough, so you can only put half the capacitor with the dielectric, and the other half is just air or vacuum, because I told you that kappa for air is the same as kappa of vacuum. Let's call this kappa, and that's just 1, a kappa of 1. Well, the correct way to think about this problem is that it's a combo. It doesn't look like a combo, but actually it is. It is a parallel combo. So let me write this. I'll put some voltage there. It's not necessary, but I'll just do it for the sake of showing. On this side, I have a capacitance which I'll call C1, and on the other side, I have a capacitance called C2, and the two of them are actually in parallel. Okay, but this one has got dielectric in it, that one does not. That one has got just air in it. So let's use the formula for a parallel case. That is C1 plus C2. So I'm going to get, first of all, let me write the expressions for the capacitance C1. C1 is going to be, let's call the area of this plate A, the whole thing, and the distance between the plates D, the usual notations for a parallel plate capacitor. So C1 equals epsilon naught A over 2 because it's half the plate area, and C2 equals kappa times epsilon naught, because there is a kappa inside, A over 2 divided by D. And since it's a parallel arrangement, I forgot to put the symbol for parallel here, CP. So we're going to use that. CP equals C1 plus C2, and that's going to be epsilon naught A over D. I have half plus kappa divided by 2. So that's going to be 1 plus kappa divided by 2 times epsilon naught A over D. When you get an expression like this, always check if the limits make sense. The limit is, imagine you just put air inside. In other words, you did not do anything. If you put air inside, kappa is equal to 1, I get 1 plus 1 over 2, which is just 1, or the same as what you would have had anyways.